Dr. Eric Pearlman. He is an observational astrophysicist whose research concentrates on the nuclei of galaxies, their physics and evolution. He has a strong record of service to the astronomical community nationwide, as well as to the academic community at Florida Tech. He oversees the Physics Resource Center, which helps students achieve greater success in physics and space sciences at Florida Tech. He maintains a large research group, including typically 3 to 4 graduate students and 15 undergraduate research assistants. And in his spare time, he enjoys chess, singing, Scrabble, reading, photography, bicycling, and working out. So ladies and gentlemen, please welcome to our dais Dr. Eric Pearlman.
Eric, let me show you you can control your show there by the forward and backwards there, I believe, okay?
Okay.
So,
Great, thanks, Mark. And you know, it's great to be here talking about this. I want to thank Mark and also Scott and Mikey and JD for putting together this remembrance of Sam Durant's. I'm going to take a second to just share a couple of things myself. Sam was somebody I knew for close to 20 years. We were hired together at Florida Tech, and we were also both Colorado grads. The two of us and one other, we were the department's Colorado Cabal. And you know, we didn't take that thing too seriously, but you know, he and I did lots of things together, you know, through the years. And I just, you know, I remember talking to him about topics ranging from, you know, science to classes. I teach a couple of the classes that he taught. I have his office. And so what I remember most about Sam actually is just his manner and his sense of humor. You know, the most understated sense of humor and the sharpest wit. That's really what I remember. So I just wanted to share that with you. What I want to talk to you about is some shocking discoveries with space observatories. I don't have a fixed agenda. We may go from item to item, sort of as your interest goes. So if you're interested in something, feel free to shout out, okay? I have more possible topics than I have time for. And so I've picked a personal selection, but if there's a particular topic here that interests you, then shout it out and we'll go on with it, okay? Yeah.
Well, we've discovered galaxies hundreds, even billions of light years away. So the light from those objects, say, let's take 110 million years at the speed of light.
Yeah.
So that light left that object 110 billion years ago. The universe is expanding at an ever-increasing rate.
Yeah.
So that object that we're looking at, the light, where is it now?
So
110 billion years have passed. Where is that object now?
So that's a really good question because two things are happening, right? The universe has continued to expand, and so it actually is further from us. But then, in addition, galaxies are moving around. Okay, our galaxy is not fixed in space. Our galaxy is part of a group of about 60 galaxies, the local group, and all the galaxies in the local group are moving around, and in fact many of you know that one of the things that's going to happen in a few billion years is that our galaxy is going to have a collision with the Andromeda galaxy. So I guess It's a long answer, but basically, we don't know because a lot can happen. That's one of the reasons why we're doing this. Let me go to a few of the things that I did want to talk about.
One more question.
Oh yeah, okay.
So,
Yeah,
everything in the sky is moving away from us.
yeah. Not everything, not things in our galaxy, but go on.
No, okay, everything out in space is moving away from
Yeah,
us.
yeah.
Some, you know, for hundreds of billions, millions of years, if, say, quantum entanglement, we could see where they are now in real time, would the sky look almost dark?
So, I don't know that I can answer that question. Part of the reason why I can't is because quantum effects only affect very small scales.
Well, I'm talking,
I understand that, but I'm, every scientist has their specialty. As an observationalist and an experimentalist, what that means is that I'm the practical guy. I'm not the theorist. So I do have to bring that down to earth a little bit.
well, my theory is if we could see all these objects in real time, the sky would be very, very dark. Everything would be so far.
Well, certainly in the future, that will be the case, but it's not yet.
I'm sorry, that's my big deal.
All right. So, what I want to do. Hello. This is not working. Okay. So, I have for you a little bit of totality this week. Okay, so this last week I was at a conference in Horseshoe Bay, Texas. Does anybody know where that is? It's about an hour west of Austin, and it was a meeting of the High Energy Astrophysics Division of the American Astronomical Society, AAS. The reason it was there is because Horseshoe Bay was near the center line of the path of totality. And so, can you play that video, please? Whoops, is it gonna play?
No, these are just pictures.
Okay, did Mark grab the video? There should be a video, something.mp4.
Dr. Pearlman?
Yeah.
While he looks, maybe a fun question. How many here were in totality Monday?
Right here.
All right, so you all know, I was too, yeah. You all know the excitement. You all know the excitement. It is, being in the path of totality is an amazing, amazing experience. This was my second time being in the path of totality, but it was the first time that I had actually seen it, because my experience in 2017 was kind of unfortunate. I was north of Charleston in 2017, and unfortunately a thunderstorm rolled in just a few minutes before totality, and so I spent totality getting rained on and running to my car.
Eric, I didn't download your video.
Oh,
If you didn't-
shoot.
Yeah, sorry about that.
Shoot, all right.
Shoot me.
All right, for those of you who are interested, that was supposed to be a video of about 40 seconds. I had clouds, okay? But it created some really interesting effects. The sun just going in and out of the clouds, and you could see the corona peeking through. It was a really interesting and exciting 40 seconds. We had a couple of, say, 45-second peaks at the eclipse. We didn't get the whole 4 minutes, but it was really exciting. I was hoping to share that with you today.
You didn't see the prominence?
So I did. I did. You could see it as a small, sort of pink.
Red.
Yeah. Well, it was more pink to me, but anyway, you know, because it was what the clouds did to it. So, can we have the next slide? All right. So, first thing I wanted to do today is I wanted to share with you this site, which you can find on the web. For those of you who have really good eyes, you can see the website. But if you Google it, it's this wonderful little site. It tells you what Webb is observing right now. And you know something? Shoot. Okay. I hate being in a seat when I'm talking, but I guess I will be. The neat thing about that is that you can see what it's doing in real time. And so you never know what it's going to be observing. When I apply to do observations with Webb, you know, I write this long proposal. But then when those things get ingested, there's a bunch of people that put together this complicated schedule. And it's published. But you never know what it's going to be observing unless you're privy to this thing. So, go to the next slide. At that particular time, this was what it was observing. That particular object happens to be an X-ray binary star, so it's a black hole that has another star circling it. Okay? And we're seeing the black hole, not because the black hole is there, but because it's accreting matter. It's taking in matter that comes from the other star. Okay? So that star is giving off matter. It's giving off matter because it has a wind. And the black hole is accreting it. What we're seeing is a combination of, number one, a disk of material that it builds up as the matter orbits it. And then number two, every once in a while that disk goes into some kind of outburst. And so we see the outburst both from the disk and also from the jets of matter that it forms. So that's what Webb was looking at that particular time. This was Thursday afternoon, as it happens. Next slide, please. All right. I also want to talk about this. So, how many people know about the Chandra X-ray Observatory? All right. So the Chandra X-ray Observatory is something that has meant a lot to me. About a quarter to a third of my career has been made on observations with the Chandra X-ray Observatory. Launched in 1999 on one of the shuttle missions. And unfortunately, it is on the chopping block in the President's fiscal year 25 budget. There are also cuts scheduled for Hubble. But Chandra is on the chopping block. And it's a shame because Chandra is still operating at peak efficiency. It is taking amazing observations. And there is no good scientific reason to cancel it. However, it's a cost-cutting measure. Basically, every 10 years, there's this decadal survey that happens, sets priorities. Of course, those priorities assume that the previous missions continue. And then the budgetary realities hit. And this is where we are at this point. And so one of the things that I hope some of you can do is to contact your congressperson, contact NASA. We don't want Chandra to be canceled. Please, let's save Chandra. It means the world to a whole generation, multiple generations of astronomers and also science fans throughout the world. Chandra has done some unique science, and in fact I want to show you some of the unique things that it has done along with the other space observatories. Can I have the next slide? So this is an image that combines Chandra and James Webb. There's a couple of things going on in this image. So the foreground to this image is a beautiful cluster of galaxies. All of those bright, extended objects are part of a cluster of galaxies. You can see them in the James Webb image. Okay? Now, if you look at the faint purple gas, faint purple emission, that is hot gas. It's gas at tens of millions of degrees. That is not within any of the galaxies. It's actually trapped in the potential well. There's an enormous amount of matter that is contained within the galaxies as well as within the space between. We wouldn't know about that diffuse hot gas if it wasn't for Chandra. And then let's go to the close-up that you see in the top part of the image. So what you can see in the top right-hand panel is a very faint galaxy. That galaxy is actually in the background to that cluster of galaxies. So it's much further away. It's actually, its light is actually gravitationally lensed, so it's much brighter than it would otherwise be. And so that galaxy is being seen less than 500 million years after the Big Bang. And so you might ask yourself, well, okay, what's so special about that galaxy? Well, it's forming stars, and oh, interesting. Look at the Chandra image. It's got some bright X-ray emission. It's got a black hole at the center that is actively accreting gas. We wouldn't know that without Chandra. Can I have the next slide, please? All right, so, oh, okay. Whoops, this was supposed to be animated. Can we do anything about that?
No, we don't have the video capability.
Okay, okay. This is a, can we go out of PowerPoint and just take away what's behind it? I'll show you why. All right, so this is, wait, huh?
It's just a picture.
Yeah, but it was a PowerPoint file that I gave you.
Right.
So,
Our computer Streamlabs wouldn't handle that, so it
I
had to be
see.
converted to JPEGs. So,
all right, well,
but we'll get on that ShuttleFest IV.
all right, well, that's too,
Yeah.
all right, so this is the X-ray view of the Crab Nebula. And it turns out it's nothing like the optical view. So that was what I was trying to show you. Let's go to the next slide. All right, so this is the X-ray view of another nearby galaxy. This is M33. It doesn't look anything like the galaxy that you see in the optical. You see the nucleus, you see some X-ray sources which happen to be X-ray binaries and things like that. All this hot gas, you don't see the stars. So this is totally different. Let's go to the next slide. All right, so this one is one of my favorites. So this is the center of our galaxy. And I'm going to go ahead and abandon the mic here because I really want to talk about this one. The black hole that's in the center of our galaxy is in here. And this is a combination of infrared and X-ray data. The X-ray is what you see here in the blue. And I just want you to just look at this because you can see that what we see in the infrared and what we see in the X-rays, they're completely different. You know, and we can't look at this in the optical because it's actually very highly obscure. Okay, 1 photon in 100 billion in the optical gets to us.
Wow.
But in the infrared and in the X-rays, we can see it. So this is what we're looking at. Okay, the black hole, like I said, is right there. And around the black hole there is a cluster of stars, and you can see them, this whole cluster here, that you can see in the infrared. You don't see that cluster in the X-rays at all. This is what the X-ray close-up looks like. Totally different. So it's just a fascinating, fascinating look. And this is what Chandra gives you that is just so unique. Let's go to the next slide. All right, so I want to talk a little bit about a controversy. This is inside baseball for people like me, but it's actually important. And this is something that we've only learned about because of space observatories. So this is what's called the Hubble constant controversy. And I want you to focus in this boxed version. This is measurements of the Hubble constant, that's how fast the universe is expanding, as a function of time. So basically, why is that interesting? It's interesting because instruments get better, measurements get better. We should converge to a single value. And we're not converging to a single value. We have two ways to measure it. One way is to use distance ladder measurements. Why do we need a distance ladder? Because we can't directly measure the distance. We'd like to use parallax. Who knows what parallax is? Yeah, parallax. That's observing an object at two different times and watching it shift. We can't do that because it's much too far away. We can do that now for stars in our galaxy out to about 10,000 light years thanks to a satellite called Gaia. Okay? All right, so what we do is we use objects in those other galaxies that are also in our galaxies. Things like, for example, Cepheid variables, which have a relationship between their period and their luminosity, or supernovae. They come up with one particular value, and those are the values in blue here. And then another measure that you can use is to use the cosmic microwave background. But if you use the cosmic microwave background, you're making a measurement up here. So this is the Big Bang. The cosmic microwave background was emitted just 370,000 light years after the Big Bang. We are down here, 13.8 billion years later. There's 13.8 billion years in between the two, and a whole lot that can happen. So this is measuring things at two different ends and trying to figure out what's going on in the middle. You all tell me how well that works. Okay? Those measurements are the yellow and orange points. They're now converging to a different value. This is a problem because if they disagree, there's actually really interesting stuff. Can we go to the next slide? Yeah, there's really interesting stuff if they disagree. Because it doesn't mean necessarily that there are two different measurements that disagree at the same time. They're made from things that are at different places. So this could actually be new physics. It could be something evolving at a different rate, and because we're measuring it at two different times, what we're seeing is the effect of the evolution in between. However, it could also be measurement errors. So this is something that is going on in real time, kind of inside baseball, but it is really captivating astronomers. Could we have the next slide? All right, another thing that is so exciting here, exoplanets. So this is something that has grown from a curiosity to a big topic. So when I was a grad student in the early 1990s, there were no exoplanets, no. Exoplanets are planets outside of the solar system. First exoplanet was found in 1995. And now there are over 5,000 known. And they were all discovered by a combination of techniques. Most of them were discovered by space observatories using transits, Kepler and TESS in particular. Again, too bad we don't have this as a movie, This is actually a combination of images from the Hubble Space Telescope of this one particular exoplanetary system. What's neat about it, and you can look this up on Google, is that, so there's roughly 20 images taken over 8 years. You can watch the planets go around it. 4 different planets, each orbiting at a different distance and a different rate. So it's neat. You can go look it up. Those planets seem to fall into lots of different categories. Categories that we never knew existed. For example, these hot Jupiters. These are planets the size of Jupiter that somehow orbit very close to their star, basically in a month or less. These are planets that we didn't know could exist. They've forced us to totally re-examine our ideas about planet formation. And we found out that the way that you get these is that planets, when they're forming, can migrate in and out. This probably happened in our solar system as well. And it's probably one of the reasons why so much of interplanetary space was cleared out of planetesimals. Other things, well, we thought they would be there. Things like, for example, rocky planets and ocean worlds and ice giants. These are, planets that might be, for example, like, the rocky planets, like the Earth, like Mars. The ocean worlds and ice giants. The ice giants might be like Uranus and Neptune, things like that. Lots and lots of stuff. One of the things that we want to know, of course, can I have the next slide, please? Which one of them could be places where life exists? We have this idea called the habitable zone, okay? The habitable zone is where we think, basically, due to how much light there is from the star and what the atmosphere might be like, where water could exist in a liquid form. Water is important because when you have life, you need a solvent. You need stuff to dissolve things in, and water is also important in the way that our bodies exist, in the way that plants exist, and so on. So water is what we base this idea around. There's 2 different notions, basically, optimistic and conservative, depending on what your model is. Are there planets inside this habitable zone? Yeah, there are. So these are planets that have been found mostly by Kepler. Some of them are in the same planetary system, so this TRAPPIST-1 planetary system, it turns out that 4 of its planets are inside what might be the habitable zone. They're close to the size of the Earth. So there are places in the universe where it might be possible for life to exist. One of the reasons why we do what we do is because we're searching for life. Can I have another slide, please? We also look at places where stars are forming. So this is a very famous image by James Webb. This is the cosmic cliffs, for those of you who know about it. It's a star formation region, okay? And I like the close-ups particularly of what's going on here. So this region here is shown here in a close-up. And what you can see is, so all of these are forming stars. Right here is a jet and shocks in the jet that's coming from this star. You have outflows of molecular hydrogen. There's a whole lot going on. We'll have a closer picture of one of these jets in a moment. It's just a really beautiful image. This is a region like where our sun formed 4.5 billion years ago. You can have the next slide, please. All right, so this is close in to a forming star. The star itself, you can't actually see it. It's down here. Okay? What are you looking at? So, stars form over many thousands of years. Okay? And what happens is that they collapse from a cloud of gas and dust. Okay? They don't collapse all at once. What happens is that the inner part collapses and then more mass starts to stream in. It forms a disk. That disk is dusty. You can see that disk right down here. Okay, this is data from Webb, by the way. Okay? What also starts to happen is that as the star forms, you start to get an outflow because the light from the star is beginning to push away the material that hasn't settled down into the disk. This is that outflow. Next slide, please. That outflow can get collimated into streams of gas like this. Okay, so the star that's powering that is down here in the middle. It's got an outflow like what you were just looking at, but it's very heavily obscured. And so what you can see are the streams of gas here and here, one on each side. We know that they are moving out because we can take spectroscopy and we use the Doppler effect. Okay? And so we know from the Doppler effect, this side is moving towards us, this side is moving away from us. Okay? Next slide, please. All right. Does anybody know this star? Yeah, you can see that star with your naked eyes. This is the first magnitude star, Fomalhaut. And it's just 25 light years from Earth. It has this really nice dust disk. It's got a planetary system that is forming. You can see some of the clumps. So this is another image from James Webb. It's actually a multi-band image. So this particular clump here is something we could only see at the longest infrared wavelengths. So a little bit about Webb. Webb is not just a replacement for Hubble. Webb is an infrared telescope. So it actually has a unique view because it operates in a different band. And so we knew this disk was there from Hubble observations. We did not know that it had this gorgeous structure which had several bands and gaps in between the bands. These belts might be where planets are forming. And in fact, like I said, you can see a clump here. We know, by the way, that this has a planet because one of the things that Hubble saw is Hubble imaged that planet, and in fact also imaged it several times and saw it moving around. Okay, next slide, please. All right, we want to know if life exists around other stars. One of the ways we can do that is by looking at those stars and the material around them. And also protostars, newly forming stars, see if we can find complex organic molecules. This is spectroscopy of this particular region, which has this completely uninformative name. But what's fascinating about it is all of these absorption lines that you can see here. Okay, so this may be tough for your eyes to see because you're kind of far away, but I'll tell you what's in here. Lines of ethanol, acetic acid, methylformate, formate ion, and acetaldehyde, and cyanate, and methane, and methylformate again. All kinds of pretty complex organic compounds. So my point is, this is not a star. This is not a planet. This is gas around a star. But this is the stuff that planets form from. the stuff of life is in there. Next slide, please. All right, Beta Pictoris here. And this is combination of Hubble and Webb data. Hubble saw this planet in the inner solar system of Beta Pictoris. It's also got this beautiful dust disk. This particular object is about 125 light years from Earth. Let's go on. Jupiter. Yes?
Dr. Pearlman, just, you know, all of us have different little bits of background here. In general, when we see these jets or the escaping stuff from a forming star, are they, since essentially everything's spinning, are they being ejected from what we consider the poles?
Yes, and what's ejecting them actually is that there's a strong magnetic field that forms in that star, and what happens is the magnetic field couples with the spin to eject the material. Yeah. Okay, Jupiter. This is a really neat image. This is a set of images, 3 different images with the NIRCam on Webb. And it turns out that these 3 different filters are sensitive to different regions in Jupiter's atmosphere. And so the neat thing is that we're looking at different regions. So this graph shows the altitude ranges that those 3 filters are sensitive to. You can see that they don't exactly overlap. So the F3360M filter, this one, is sensitive to the outermost regions of the atmosphere, and these other 2 are sensitive to other regions in the middle and then further in. So you're looking at different regions, and you're looking at the winds in different regions and where they are, not just in terms of how fast they're moving, but what level of the atmosphere they're in. It's really fascinating. Let's go to the next slide. All right, so this particular object, a little personal story to tell you about. My daughter is a student who is currently entering grad school. She'll be starting at Arizona State for grad school in the fall. She's interested in planetary geology, and one of the reasons she's interested in it is because she's interested in climate history and the history of life throughout the solar system's history. Enceladus is very interesting because it has a subsurface ocean. One of the reasons we know it has a subsurface ocean is because we can see these outflows. So this is an image of Enceladus. Enceladus has outflows. This is a close-up on Webb data. Enceladus is here. There was a plume emitted from it. This is the plume. Webb took spectroscopy of it. And what it did is it had several apertures, one aperture here, one aperture here, and then an aperture on Enceladus itself. And you can compare the 3. And there's water emission in all 3. All of these lines are from water. And so we know that there's water. There's also other stuff in that. Can we have the next slide? All right, we're going to shift from our solar system out to the most distant galaxies. We're going to go again. This is another cluster of galaxies. And we're going to use that as a lens, right? So one of the things that a cluster of galaxies can do is that because there's so much matter, its gravity can focus the light from things that are further back. And so, yes, there's all these interesting galaxies here from the cluster, but if we focus in on some of the really faint objects, they turn out to be very distant galaxies, these 2 in particular, which are at random locations. Let's see, number 1 happens to be right here. Number 2 happens to be in here. Couple of things that you notice. So first of all, number 2, you know, they're very red, both of them. Number 2 and number 1, they look different, right? This one is very extended. It's got this weird amoeba-like shape that looks very different from anything that we see. Why is that? It's because matter was still streaming into those galaxies. And what we're seeing are the densest parts that are forming stars. Let's go into the next slide. So this is a comparison of what we see. This is actually an image many of you have seen probably before. Okay, this was one of the original 5 that was released from Webb. This is Hubble's view of that galaxy cluster. This is Webb's view. Okay? Now, 2 different bands, okay? Because this is near infrared, this is optical. But you can see how much deeper Webb goes. And this is in far less exposure time, by the way. Another thing that's just amazing is all of these arcs. These are distant galaxies that have their light lensed by the cluster. They are arcs. You can imagine the light coming from behind. Hold up a glass to a light. One of the things that you see is that you see the light passing through the glass form arcs. Same thing is happening to the galaxy. The galaxy is, you know, it's back here someplace. These are all images of that galaxy. In fact, if we trace out a circle at a specific place that is centered on where the center of mass is, those are all images of the same galaxy. So this, and let's see, that one, maybe this one, I don't know, but definitely this one and that one and that one, those are all the same galaxy. The light just took different paths to get to us. All of those galaxies are far in the background. Next slide, please. All right, I'm going to skip this one because this one, unfortunately, was a fly-through of a particular cluster, a particular deep field where you could see each of the galaxies. If we've got that on the disk, I'll show it to people later. Let's go to the next slide. All right, so does anybody know this object? All right, so the sky is not a fixed thing. This is a supernova that happened in the Large Magellanic Clouds. This is the largest satellite of our galaxy, about 150,000 light years away. We saw the light from that explosion in 1987. This is supernova 1987A, for those of you that know that. This is the remnant from that. Why is it the remnant? Okay, the supernova happened. All the gas from the star, except its core, was thrown out at speeds of 10, 20,000 kilometers per second. Moves really fast, right? Well, it expands out into interstellar space. This is the expanding shock from that star. There's also some arcs here, which are from a previous episode of mass loss from the star, like 10,000 years ago previous. Okay? So this is the shock. This is the expanding gas from the explosion. Now, it's got all of these neat knots in it because it's also interacting. So the previous mass loss, it had left features in the interstellar gas. This is bright because it ran into one of those features. And so you can see the two gas streams interacting. Let's focus in now on what's in the center. So, for 50 years, excuse me, because this was 1987A, we've wondered, was there a remnant of the star, a pulsar, which was the collapsed core of the star that exploded? We didn't know. We hadn't found it. And actually, an interesting story from when I was a college student, an undergraduate. I was interning at the Jet Propulsion Lab in 1987, 1988, and 1989. Okay? So I was in a radio astronomy project. One of the things that I remember in it was 1988. 1988, I remember we were working with one of the Australian teams. It was a project that was working with radio telescopes in Australia. And they said, we had this interesting signal. We think we've discovered the pulsar. They hadn't. They hadn't. And this is a great example. You know, they were talking about the things that you have to do during a mission, also the things you have to do during an observing run. It turns out they hadn't correctly accounted for 60 cycle current. And what they were seeing was noise from the outlets and all the other electrical machinery that was in the room and in the telescope. It was 60 cycle noise. So we threw that away. All right. However, pulsars are bright in X-rays. One of the ways that we can see if a pulsar is there is by looking at lines from highly ionized atoms. There's something there. This has to be confirmed. So one of the things that now has to be done, this is nice, fresh data. This discovery was announced about 2 months ago, literally. When I say fresh, I'm not kidding. But this now has to be confirmed by further observations by radio telescopes in Australia. It has to be done from the south because Large Magellanic Cloud, for those of you that know, we can't see it from here. It's at minus 67 degrees south, so we can't see it. But in Australia, or South America, they can see it. Plenty of radio telescopes in Australia. So they're going to be looking at this to confirm whether there is a pulsar here. Fingers crossed.
Yeah.
Next slide. All right, so I love this image. This is Cassiopeia A, the remnant of a supernova that happened several hundred years ago. The star was somewhere in there. And what I really like about this, so this is James Webb images, and this is 2 different bands. This is the near infrared, this is the mid-infrared. They're very different. They are very different. And so you're looking at the gas that came from the explosion, but there's different parts that are bright in different bands. Let's go to the next slide. All right, I'm going to finish up here with a few images of nearby galaxies. And let me explain to you what's going on. This is a combination of 2 images. Okay? What you're looking at on the left is Hubble imaging. Okay? And then what they've done is that they've separated it with a diagonal line, and on the right, you're looking at James Webb infrared imaging. So it's the same galaxy, 2 different sides that you're looking at, optical one side, infrared on the other. And you're looking at some very different things on the 2 sides. All the stars and the dust here, and then transport this dust over to the other side, it glows in the infrared. Why? Because of the light coming from all of these stars. It's heated up. It has to re-emit that light someplace else. It re-emits it in the infrared. Come over here into the nucleus. We're seeing that region much better in the infrared than we do in the optical because we're peering through the dust. This is a spiral galaxy pretty similar to our own spiral galaxy. I forget the catalog number of this spiral galaxy, but it's not terribly important. Somebody might know it. It's not terribly important. The other thing that's really interesting is, so what they've done is they've created this effect by reshading each image. So you can still see the optical on the right, and you can see a little bit of the infrared on the left. I like to focus in on here, because this is a star, or a star-forming region. You can see the shell of infrared gas around it. Let's go to the next slide. All right, here's another galaxy. I just picked these at random. Same kind of thing. Again, we're going to divide this way, and the optical, the HST, the Hubble image is over here, and the infrared is over here. Again, just realize how different they are. So when you're looking at different bands, I don't just want you to take away that Webb is a better telescope. It is, right? It's a much better telescope because it's bigger. And it's in this great orbit at L2, which is far away from interference. But it's in a different band, and because it's in a different band, you're looking at different things. You're looking at the stars here. You're looking at the gas here. Okay, next slide. I think that's the last one, this last one. This next one. Is there one more?
That was it.
All right. I thought I had one more. Anyway, I'm happy to take some questions. Yeah.
Thank you there, Eric.
I've read that the Webb telescope is challenging a lot of long-held beliefs in the astronomical community.
Yes.
And that there is some resistance within the community toward Webb because of that fact. Is that true? And if so, can you speak to it?
So, Webb is certainly challenging a lot of the long-held notions that we had. Actually, the resistance to Webb, some of it is because of controversies about, how Webb and how NASA treated certain minorities in the past. And it's something I really don't want to get into, but it's something that is...
My discussion is the resistance to the science coming back from...
So, fair enough. And personally, this is something that, it happened with Hubble as well. Okay? If we go back to the Hubble constant controversy, which I talked about 15 minutes or so ago, one of the things that was going on is that there was this project, a set of key projects that Hubble had to actually measure the expansion of the universe. There were two communities at the time. When Hubble revealed its first observations, there was resistance because it turns out that both communities were getting challenged. Because, this should be no surprise, the value that was being found was somewhere in the middle. Both communities said, well, this is wrong because of X, Y, Z, Well, my point in saying that is that I don't view this as something that is irrational. I view this as the process of science working. I've been around in science long enough to realize that scientists do not move all at once. Science gets done slowly over time, and you have to do lots of careful observations. You need new ideas, new theoretical ideas to go along with them. Rinse and repeat. You do more observations, get new things that come out, and so really it's a process. I mentioned that I was hired at the same time as Sam. But there's a generation in between us. Okay, I'm in my mid to late 50s, and so there was a generation in between Sam and me. There's also a generation in between me and the new generation of astronomers who are just getting out of grad school, and they're in their late 20s or early 30s. And so I'm in that generation that can see both, and I've got enough history, right, 30 years in the field now, that I know how the field has evolved. That's what's going on here. I really don't think that It's extraordinary. Well, okay, it's extraordinary because of the range of new things that Hubble and that Webb is finding. But the way it's happening is not extraordinary. Yeah.
Quick question about our black hole in Sagittarius.
Yeah.
How do you say the name of that?
I say Sagittarius A star, or Sag A star.
Don't some people say Sagittarius A prime?
I haven't heard that one. I haven't heard that one.
Because then saying star, isn't that redundant?
So yes and no. So history, and I'm old enough now to be in the history mode. It's called Sagittarius A star because of early radio surveys, and Sagittarius A was the brightest radio source of the constellation Sagittarius, and the star is what's in the center, basically. But for those of you that don't know, we know that there's a black hole there because of a couple of sets of observations. First of all, there were observations that were done during the 2000s, 2010s, where they looked at the stars that were circling the black hole. You could see them move around. And so they're all orbiting this dark, almost unseen mass that is at the center. And you can use the motion of those stars to figure out how massive it is. Prediction that was made was about 4.2 million times the sun's mass. Fast forward to the late 2010s and a paper that was written just during the last few years, came out last year. We have observations from an array of microwave telescopes called the Event Horizon Telescope. And we have the photon ring around that black hole. There are two objects where the photon ring has been found. One is Sagittarius A star, and the other is the black hole at the center of the galaxy M87, which I happen to have spent a lot of time on in my career. That is how we know that there is a black hole. And when you combine the two, it kind of cements it. Are we done? Do we have time for one more question? Go ahead.
Yeah, we'll take another question. I'm gonna
Okay.
come over here and get people off to lunch, Nick. And,
Sounds good.
I was just gonna ask, on that topic,
Yeah.
I was zero about astronomy.
Yeah.
Other than the stars are pretty. Is there a black hole at the center of every galaxy? Is that how they start their formation?
So I'm going to answer that in two parts. Yes, there is a black hole at the center of most every galaxy, but it's actually a big question mark as to whether that's how they start or whether the black hole forms as part of the process of forming the galaxy, because that whole process is not clear. It may happen that the galaxy forms and the stars begin to form, and then the center collapses in that process, and then later you have a black hole. That's one of the reasons why, if we look at those first few images that I showed you, and we look at that one image with the very distant galaxy, and Chandra showing us the black hole in the center by its X-ray emission, those observations are showing us how far back we see those black holes. The question is, if we go further and further back in time, will we see the galaxies, but not the black holes? Or the other way around? That's going to be the answer to the second part of what you just said.
let's give Eric a big hand here. Thank you. My favorite astronomer
I
there.
want to thank Dr. Pearlman for a fascinating discussion. I mean, this was just eye-watering today. Thank you. Thank you very much.
Thank you.